Right now, you live inside a region of space that is about 93 billion light years across, and everything you will ever be able to see is inside that region with you. This is what scientists mean by the observable universe, a size we get from the age of the universe and from how fast space has expanded since the Big Bang. But before we continue, please subscribe to the channel to give your support. Let's continue. To make that clearer, start with one idea. What is a light year? A light year is the distance light travels in 1 year, moving at about 186,000 miles per second, or about 300,000 kilometers per second. Over a year, that is roughly 5.9 trillion miles, or about 9.5 trillion kilometers. Now take that distance and imagine it repeated 93 billion times. That gives you the approximate width of the part of the universe whose light has had time to reach you so far. This is not just your galaxy. It is the full spherical volume around you that can send light to your detectors. But a problem shows up immediately. The universe is about 13.8 billion years old, so how can anything end up tens of billions of light years away already without breaking the speed limit of light? At first, that sounds impossible. The key is what distance we are talking about. When cosmologists say the radius of the observable universe is about 46.5 billion light years, they mean the distance to those far galaxies today, if you could freeze the expansion of space and measure it right now. While the light was on its way here, space itself was stretching, increasing the distance between us and those galaxies. By the time the light arrives, those galaxies are much farther away than just light speed times travel time. Once you know the radius, about 46.5 billion light years, the diameter is twice that, around 93 billion light years across. That detail matters because it fixes your mental picture. You are not near the edge of this region. You are very close to the center of your own observable sphere, because by definition, you draw that sphere around yourself. An observer in a distant galaxy would draw their own observable bubble, centered on them, with about the same radius. They would see a lot of the same structures we do, but not exactly the same set. Now separate two ideas, the observable universe and the entire universe. The observable universe is just the part of space that has had time to send us light since the Big Bang. That boundary is a horizon set by time and expansion, not a physical wall. Beyond that horizon, space almost certainly continues with more galaxies and more structure, but light from there has not had enough time to reach us, and some of it never will. So when you hear 93 billion light years across, do not picture an edge where space stops. Picture the current limit of what we can observe or measure. This leads to a simple question. Inside this gigantic bubble, how far have humans actually traveled? With hardware, not with light, but with real objects. The honest answer is almost nowhere. The farthest any human being has gone is to the moon, about 240,000 miles away, or about 386,000 kilometers. In terms of light travel time, that is about 1.3 light seconds. That's the maximum distance for human travel so far, 1.3 light seconds out from the planet. You might say, fine, our robotic spacecraft have gone much farther, and they have. But the comparison is still harsh when you put it next to 46.5 billion light years. The most distant spacecraft we have, Voyager 1, is roughly 15 billion miles from Earth. Light takes on the order of 22.5 hours to travel from here to Voyager. That is less than one light day. Stack one light day next to tens of billions of light years, and our entire spacefaring record rounds down to almost zero. Our entire spacefaring record sits in a tiny region right near the center of the observable sphere. On cosmic scales, we have barely moved. So if we have only covered a microscopic distance compared to the size of the observable universe, how do we know anything about that huge volume? How can we quote numbers like 46.5 billion light years for the radius with any confidence? The answer is that we do not need to travel there because light has already done the traveling for us. Every photon that arrives here, whether it's microwave background radiation, visible light from a nearby star, or red-shifted infrared light from a distant galaxy, carries information. It tells us when it was emitted, how much space has expanded while it was on the way, and what kind of object produced it. For decades, the main tool for turning that light into a map was the Hubble Space Telescope, orbiting a few hundred miles above Earth. Hubble looked mostly invisible and ultraviolet light, with some near-infrared. It showed that the universe is filled with galaxies at all distances, and pushed our view back to when the universe was only a few 100 million years old. Beyond that, the light from earlier galaxies was shifted so far into the infrared by expansion that Hubble could not see it. The first generations of galaxies and stars, forming in those early hundreds of millions of years, were mostly hidden. This is where the James Webb Space Telescope changes things. Webb is built to see in infrared, where that stretched, ancient light now appears. It is sensitive enough to pick up very faint, very distant galaxies, and not just detect them, but study their light in detail. Each deep Webb image is a slice through billions of years of cosmic history, with nearby galaxies, mid-distance galaxies, and very early galaxies all stacked along the same line of sight. By collecting many of these slices in different directions and combining them with data from other observatories, we can start to build a three-dimensional map of what actually lives inside our observable bubble. But that brings you back to the confusing point that started this section. If the universe is 13.8 billion years old, how can any galaxy already be 46.5 billion light years away? And how can Webb look at light that has been traveling for more than 13 billion years without breaking the rule that nothing outruns light? To answer that, you have to rethink what you mean by distance in an expanding universe, and you have to see how astronomers use redshift, the stretching of light's wavelength, as a kind of ruler. That is the next step, and once you understand it, the 93 billion light-year number stops sounding like a mistake and starts sounding like a measurement. You're told nothing outruns light, so how can anything in this universe end up 46.5 billion light years away when the universe itself is only about 13.8 billion years old? It sounds like the numbers are breaking the rules. Let's go through what's actually going on, in normal language. A light year is just a distance. It's how far light travels in 1 year, moving at about 186,000 miles per second, about 300,000 kilometers per second. Over a year, that's about 5.9 trillion miles, about 9.5 trillion kilometers. So a billion light years is just how far light gets in a billion years in empty, non-expanding space. In that simple case, distance equals speed times time. But on the real, large-scale universe, space itself is not fixed, it stretches. Here's the key point. Light moves through space at the speed of light, but space itself is allowed to expand. Physics does not forbid that. General relativity says the geometry of space can change with time. Distant galaxies can be carried away from us by that expansion. They are not blasting away faster than light with engines. They mostly sit in their own neighborhoods while the space between us and them stretches and increases the distance. Now bring in a word cosmologists use all the time: co-moving distance. Co-moving distance means how far apart are 2 points right now if you could freeze the expansion of the universe at this instant and measure the gap. It ignores the past history and just gives you the current separation in today's stretched universe. When scientists say the radius of the observable universe is about 46.5 billion light years, that's the co-moving distance from us to the farthest places we can see. The balloon picture is just a quick way to visualize this. Imagine the surface of a balloon as space, and tiny dots on it as galaxies. As the balloon inflates, the dots move apart, not because they're sliding, but because the rubber is stretching. If you keep each dot glued to its patch of rubber, their co-moving positions are fixed, even while the distances grow. Our universe works the same way in 3 dimensions, with galaxies stuck in expanding space. Next idea. Look-back time. Look-back time is how long has that light been traveling before it hit our telescope. If we say the light from a galaxy has a look-back time of 13.4 billion years, that means the photon left 13.4 billion years ago and arrived now. But when it started its trip, that galaxy was much closer than it is today, maybe only a few billion light years away. While the photon was moving, the universe kept expanding, stretching the space between us and the galaxy and stretching the wavelength of the light. So here's the weird sounding but correct situation. The photon traveled for 13.4 billion years, but the object it came from is now much farther than 13.4 billion light years away. Depending on the expansion history, that galaxy's present distance might be 30, 40, or even more than 40 billion light years. Nothing about that breaks the speed limit. The photon never went faster than light. It always moved at the same maximum speed. It's just that while it was in flight, the ruler underneath it was getting longer. This is where the James Webb Space Telescope becomes essential, because we can't lay down a giant measuring stick. We use light as the ruler, and the main thing Webb reads is redshift, written as the letter Z. Redshift is how much the wavelength of light has been stretched by cosmic expansion on the way to us. Bigger redshift means more stretching, which usually means the light has traveled longer and the source galaxy is farther away in co-moving distance. Take an extreme example. Webb has found galaxies at redshifts around 14, like one candidate called GNZ14. A redshift of about 14 means the wavelength of the light has been stretched by more than a factor of 15. Put that into our best expansion model, and you find we're seeing that galaxy as it was only about 280 million years after the Big Bang. If you then ask, where is that galaxy right now, the answer is not 280 million light years away. Its present distance is tens of billions of light years, well beyond 30 billion, because space has kept expanding for over 13 billion years since that light left. So redshift tells us two things at once: how far back in time we're looking and how far away the object sits in today's universe. Webb is powerful because it can detect very high redshift galaxies and take spectra of them, splitting their light and measuring the redshift precisely. That lets astronomers turn redshift into both a look-back time and a co-moving distance. That is how we know that our observable universe, the region from which light can reach us, has a radius of about 46.5 billion light years. Now back to the main question. Is the 93 billion light-year wide number a mistake? No, it comes from three basic facts. The universe has a finite age of about 13.8 billion years, light has a fixed speed, and space has been expanding the whole time. If the universe had never expanded, the farthest thing we could see would be about 13.8 billion light-years away. Because the universe has stretched, the stuff that emitted the earliest light we can detect has been carried much farther away since that light started moving. Nothing has outrun light locally. No spaceship, no galaxy, no signal has broken the speed limit in its own patch of space. The only thing moving apart faster than light is the separation between very distant points, because new space is being added in between. That is allowed by relativity. It doesn't let you send a message faster than light, it just means the map itself is stretching while you're trying to read it. And this is what James Webb is now turning into data. Those deep fields full of tiny red smudges are not just pretty backgrounds. They are a record of how much the universe has expanded, how fast structure formed, and how far away those first generations of galaxies really are today. Once you accept that space itself expands, the idea of a 93 billion light-year wide observable universe stops being a glitch in the story and becomes a measurement we can check. So now you know how you can have a 46.5 billion light-year radius in a 13.8 billion year old universe. The next question is, what kind of telescope do you build, park it 1,000,000 miles, 1.6 million kilometers from Earth, and ask it to see the faint heat of baby galaxies only a few 100 million years after the Big Bang? You're looking at a telescope so sensitive it could spot a bumblebee's body heat on the moon from Earth. Except this thing isn't even near Earth. It's sitting about 1,000,000 miles away, and it's doing that level of sensitivity to the entire universe. That's the James Webb Space Telescope. When you see those sharp, deep images online, it's easy to think, nice camera. But this is a purpose-built machine to bend your sense of time, to pull light from the first few 100 million years of cosmic history and turn it into data you can actually analyze. Start with the obvious feature, that giant golden mirror. Webb's primary mirror is about 21 feet across, 6.5 meters. It's not one solid disk, it's 18 separate hexagonal segments made of beryllium, each coated with a very thin layer of gold so they reflect infrared light efficiently. When all 18 segments are aligned, they act like one huge mirror with more than 6 times the light collecting area of the Hubble Space Telescope. That extra area is everything. More collecting area means more photons per second from faint, distant galaxies. It's like the difference between a small backyard telescope and a professional observatory, pushed to the extreme. When you're trying to see galaxies that are barely there above the background noise, that factor of 6 is the difference between no detection and we can actually measure a spectrum. But a big mirror is not enough if you're looking for the oldest light. The key trick is what kind of light Webb sees. It's tuned mostly to infrared wavelengths, not the visible light your eyes use. Because the universe has been expanding for 13.8 billion years, light from very distant galaxies gets stretched to longer, redder wavelengths as it travels. By the time it reaches us from a galaxy at extremely high redshift, that light has moved out of the visible range and into the infrared. A normal optical telescope basically misses it. Webb is designed to catch exactly that stretched light, the stuff from the earliest galaxies and stars. Infrared also has another advantage. It can pass through dust that would totally block visible light. Our own galaxy is full of dust clouds, and so are many distant galaxies. To an optical telescope, those regions look dark or murky. To Webb, they become transparent enough that you can see what's forming inside. Young stars, star-forming regions, and the structure of galaxies that are still assembling. That's why so many Webb images show fine detail in places that used to look like vague blobs. You're not just seeing more, you're seeing in a different part of the spectrum where the early universe is actually shining. Now, where do you park a machine like this so it can work properly? You don't leave it in low Earth orbit like Hubble. Webb sits near the Sun-Earth L2 point, about 1 million miles away, about 1.5 million kilometers, on the night side of Earth, roughly 4 times farther than the Moon. L2 is a spot in space where the gravity of the Earth and the Sun plus the spacecraft's orbital motion balance out in a way that lets Webb stay in a stable orbit around that point. From there, the telescope can keep the Sun, Earth, and Moon all on the same side, behind its sunshield, so its instruments always face deep, cold space. That sunshield is as important as the mirror. It's a stack of 5 thin layers, each about the size of a tennis court. Its job is simple: block heat. Infrared detectors are basically heat sensors, so if the telescope itself is warm, it swamps the faint signals from distant galaxies. Webb has to stay extremely cold, around minus 370 degrees Fahrenheit, about minus 223 degrees Celsius, for many of its instruments. The combination of the L2 orbit and the multi-layer sunshield lets its mirrors and instruments cool down to those temperatures without using a huge amount of active cooling. On the hot side, facing the sun, you've got a spacecraft at hundreds of degrees. On the cold side, where the mirror and instruments sit, you're only a few tens of degrees above absolute zero. That temperature difference is what makes Webb useful. Inside that cold zone are the instruments that actually turn photons into science. First is NIRCam, the near-infrared camera. This is Webb's main imager in the near-infrared range, and it's what produces a lot of the deep field pictures you've seen, packed with galaxies. It doesn't just take pretty images, it also helps find high redshift galaxy candidates by looking at how their brightness changes across different filters. Then there's NIR-SPEC, the near-infrared spectrometer. This one is crucial. Instead of just taking pictures, NIR-SPEC spreads a galaxy's light out into a spectrum, splitting it into thousands of wavelength spins at once. That spectrum lets astronomers measure redshift very precisely by seeing how known features like hydrogen emission lines are shifted. The same data also reveal chemical fingerprints like oxygen, nitrogen, and other elements, so you can tell what kind of stars have already lived and died in that galaxy. You also have MIRI, the mid-infrared instrument, which covers even longer wavelengths. MIRI is especially good for seeing cooler dust, very distant redshifted objects, and structures that glow in the mid-infrared. Together, these instruments let Webb act like a combined camera and lab, not only detecting distant galaxies, but telling you when they're shining, how fast they're forming stars, and what's already happened inside them. Now, zoom out from the hardware and look at the timeline. Webb launched on December 25, 2021, on an Ariane 5 rocket from French Guiana. After launch, it had to unfold in space. The sun shield had to deploy, the mirror segments had to swing out, and all of that had to happen perfectly because there is no way to send a repair crew a million miles out. Over the next few months, the team slowly aligned the 18 mirror segments using tiny actuators, turning 18 separate reflections of a star into one sharp point. They cooled the instruments, tested the systems, and tuned everything until the telescope was ready for science. By mid-2022, Webb released its first full-color images and spectrum. These weren't just publicity shots. In those very first datasets, you already had galaxy clusters acting as gravitational lenses, deep fields showing galaxies at extreme redshifts, and spectra that confirmed just how far back the telescope could see. Within days of starting science operations, Webb was pushing the frontier into the first few 100 million years after the Big Bang, exactly the window that had been out of reach before. So now you have this machine, a 21-foot golden mirror frozen at minus 370 degrees Fahrenheit, sitting a million miles from Earth, tuned to infrared, splitting ancient light into spectra. The natural question is, what happens when you actually point it at a blank-looking piece of sky and stare for hours? What do you find when you give this thing the chance to show you the early universe? Because that's where the story gets uncomfortable. Very quickly, Webb started seeing galaxies that looked too bright, too massive, and too put together for how young the universe was at that time. Almost like the early universe was building things faster than our models said it should. Within weeks, you point this brand new telescope at the sky and you start seeing galaxies that basically should not exist yet. It's like walking into a hospital nursery and finding a 40-year-old bodybuilder lying in the crib. The universe is supposed to take its time to build big, bright galaxies. Webb is saying, nope, some of them showed up fast. Let's start with one clear example, Maisie's galaxy. It comes from a Webb program called CEERS, the Cosmic Evolution Early Release Survey. Astronomers took deep images in infrared, ran the data, and one object stood out. Later, with follow-up and analysis, it landed at a redshift of about 11.4. In simple terms, that redshift tells you how much the universe has expanded since the light left that galaxy. When you convert that into time, you're seeing Maisie's galaxy as it was only about 390 million years after the Big Bang. The universe was roughly 2 to 3% of its current age. And yet, this is not some tiny, barely there smudge. It looks like a real organized galaxy already producing stars. Think about what that implies. In less than 400 million years, gravity had to pull gas together, cool it, form the first stars, enrich the gas with heavier elements from those stars, then build up a galaxy bright enough for Webb to detect across more than 13 billion years of look-back time. That is a tight schedule. In the models we used to run before Webb, we expected things to grow, but not always at this pace, not with this level of brightness so early. Then Webb pushed even further. Surveys like JADES, the JWST Advanced Deep Extragalactic Survey, started turning up galaxies at redshifts around 13 and higher. One famous example is JADES-GS-Z13. Another is MOM-Z14 from later work. These aren't just best guesses, they have spectroscopic confirmation, meaning Webb or other instruments spread their light out into a spectrum and measured the exact shift of known features. Those redshifts above 13 put these galaxies only about 280 to 330 million years after the Big Bang. At that time, the universe was extremely young. We're talking a few 100 million years into a timeline that now spans 13.8 billion years. Yet these galaxies are not invisible wisps. They show up as clear detections in Webb's deep images. When astronomers estimate their properties, they find that many of these early galaxies are relatively bright and, in some cases, already fairly massive in stars. Here's what too bright means in practice. You take the light from one of these galaxies, fit it with models of stellar populations, and you find star formation rates of tens to maybe over 100 solar masses per year. That means in 1 year, the galaxy is turning gas into new stars with a total mass of tens to hundreds of times the mass of our sun. In the present-day universe, that is energetic but not unheard of for starburst galaxies. But seeing that level of activity when the universe is only a few 100 million years old is a serious surprise. Standard galaxy formation models predicted more modest, slower growth at those early times. On top of that, some of these systems seem to host stellar masses that are already comparable to or above those of small present-day galaxies. We're not talking about a few thousand suns, we're talking about hundreds of millions or more. You can adjust the details. Maybe the mass estimates are on the high side, maybe the exact star formation rate has some uncertainty. But even with conservative assumptions, the picture is clear. Galaxies were building up faster and shining brighter in the early universe than many simulations expected. Now, you might wonder, are we sure these are real galaxies at those distances? Or not just some kind of measurement error, a weird foreground object, or a misidentified source? This is where Webb's spectra matter. For some early candidates, astronomers only had photometric redshifts, which are estimates based on how bright an object is in different filters. Those can be wrong, but for key objects like JADE's GS Z130 and MOM Z14, teams have used instruments like NIRSpec on Webb to take actual spectra. In those spectra, you see specific emission lines, for example from hydrogen or oxygen, shifted to the red by a very precise amount. You measure that shift, you get redshift, Z. You plug that into the cosmological model, and you get the look-back time and the cosmic age. That is why these galaxies can't just be dismissed as artifacts. They show clean spectral signatures. The lines line up. The redshift checks out. These are real galaxies, sitting at extreme distances, already active. Another detail that makes this even more interesting is the presence of metals, meaning elements heavier than helium in some of these early galaxies. When you pick up oxygen emission lines only a few 100 million years after the Big Bang, that tells you there have already been earlier generations of stars that formed, burned through their fuel, and exploded as supernovae to seed heavier elements into the gas. So by the time you see these bright Webb galaxies, you're not looking at the first ever stars. You're looking at a second or third wave already running on processed material. Again, that points to a rapid, intense early phase of star formation. So what's the problem exactly? Why does this make cosmologists nervous? It's not that the whole picture of the universe is broken. On large scales, the standard model of cosmology with dark matter and dark energy still matches the cosmic microwave background and the overall distribution of galaxies very well. The tension is on the small, early scales. When you run detailed simulations of structure formation starting from those early conditions, and you ask how many bright, massive galaxies should I see at 300 million years, you often get fewer and fainter systems than Webb is now finding. Early on, headlines started using phrases like impossibly massive galaxies. As the data have improved and mass estimates have been refined, a lot of those claims have been toned down. Many of these galaxies are not literally impossible for the model once you include uncertainties. But even after the dust settles, you still see the same trend. The early universe looks busy. There are more bright, star-forming galaxies at high redshift than many people expected. That leaves you with a too-fast universe problem. Either galaxies were assembling their stars more efficiently than we thought, maybe converting gas into stars at higher rates, or feedback processes like supernova explosions were less effective at blowing gas out of small galaxies, or the structure of dark matter halos at early times is different from what simple models assume. In other words, something in the recipe for early galaxy growth needs to be updated. And here's the tension that drives the next part of the story. If galaxies are this active, this early, then the first few 100 million years of cosmic history are not quiet at all. They're a period of intense star formation and rapid buildup. So what does that actually look like if you zoom in on the physics of those galaxies? How dense are those star-forming regions? How fast are they converting gas into new suns? And how does that behavior tie into the bigger picture of the universe switching on its first light? That's where we move from individual surprising galaxies to a bigger idea, the early universe as a kind of cosmic baby boom, a period where star factories at the edge of time are running almost non-stop. You're watching the universe in its toddler years, and it's hyperactive, it's forming stars like there's no tomorrow, and James Webb is the thing letting you see it. This early phase is not calm, it's not gentle, it's loud and busy in terms of physics, and a lot of what Webb is showing us is that the first galaxies are basically extreme star factories. Start with the numbers. When analysts analyze some of these high redshift galaxies, the ones Webb finds at redshift 10 and beyond, they estimate star formation rates of tens of solar masses per year, sometimes pushing towards 100. That means each year, these systems are turning enough gas into stars to equal tens or hundreds of suns. That may not sound insane until you compare it to the Milky Way, which forms only a couple of solar masses of stars per year spread over a disk of 100,000 light-years across. These early galaxies are doing similar or higher rates packed into regions only a few hundred to a few thousand light-years wide. You're taking Milky Way-level activity and cramming it into a much smaller volume. That's what starburst really means here: dense gas, short timescales, and very high output. Now, look at their total mass in stars. Some of these galaxies at redshift greater than 10 already have stellar masses similar to present-day dwarf galaxies, or even close to the Small Magellanic Cloud, which orbits the Milky Way and has a few billion solar masses in stars. But the key difference is timing. The Small Magellanic Cloud had the full 13.8 billion years of cosmic history to grow and evolve. These early galaxies are reaching similar masses when the universe is only 2 to 3% of its current age, a few 100 million years in. That means gravity, cooling, and star formation all had to operate very efficiently, with gas flowing into dark matter halos and being rapidly converted into stars without being blown out or shut down too early. In astronomy, when we say metals, we mean every element heavier than helium. Those elements don't come from the Big Bang. They are produced inside stars and spread into space by stellar winds and supernova explosions. Webb spectra for objects like JADE's GSZ14 are now picking up signatures of oxygen and other metals just around 300 million years after the Big Bang. That tells you at least one full cycle has already happened. Massive stars formed, burned through their fuel in just a few million years, exploded, and dumped heavier elements into the gas. Then, new generations of stars formed out of that enriched material. This is important for feedback. Massive stars put out intense radiation, strong winds, and finally, supernova blasts. All of that can push gas away, heat it up, and in many simulations, it slows down or even stops star formation in small galaxies. But Webb is seeing systems that, despite that feedback, are still cranking out stars at high rates. So either the feedback is less effective in these first galaxies than we thought, or the gas supply is being replenished quickly enough from the surrounding cosmic web that they can keep going. In either case, the early universe is not a fragile, easily disrupted environment. It's more robust and more active than many models assumed. Now, connect this directly to the big picture: reionization. After the universe formed neutral hydrogen and released the cosmic microwave background, there was a long stretch often called the cosmic dark ages. There were no bright galaxies yet, and the hydrogen gas between future galaxies was mostly neutral, meaning it absorbed high-energy radiation very effectively. When the first generations of stars and galaxies ignited, they started pumping out ultraviolet light. Some of that light escaped their galaxies and traveled out into intergalactic space. Those photons had enough energy to knock electrons off hydrogen atoms, ionizing the gas. Do that over and over across many galaxies, and you start carving out ionized bubbles around each one. Over a few 100 million years, those bubbles grow and overlap, gradually transforming the whole universe from a mostly neutral fog into a mostly ionized transparent medium. That process is what we call cosmic reionization, and it likely wrapped up by around a billion years after the Big Bang. The galaxies Webb is finding at redshifts 10, 12, 14, with their intense star formation, are exactly the kinds of objects you'd expect to be driving that change. The key question is, who did most of the work? A huge number of small, faint galaxies, or a smaller number of relatively bright ones? Webb is now pushing into the regime where you can start to answer that. If these early galaxies are as common and as productive as they seem, they could have produced enough ultraviolet photons to ionize large regions of space much earlier than some models predicted. That would shift the timeline for when the fog of neutral hydrogen really started to lift. It would also change how we interpret measurements of the intergalactic medium from other telescopes. All of this points in the same direction. The early universe was more chaotic, more clumpy, and more efficient at turning gas into stars than the older, smoother pictures suggested. Instead of a slow, gentle ramp-up, you get rapid growth, strong bursts of star formation, and quick recycling of material through supernovae. That has knock-on effects for everything: the formation of the first black holes, the number of small galaxies that survive to later times, and the chemical makeup of the gas that later generations of stars and planets will form from. And here's the problem this creates for theory. For decades, cosmologists have used huge simulations to grow universes in computers, starting from the conditions we see in the cosmic microwave background. They tune those models so that, by the present day, the distribution of galaxies and large-scale structure matches what we observe. Now, Webb is shining a light into the first few 100 million years and asking, did your simulated universe actually build galaxies this fast, in this many places, with this kind of star formation? Or is your recipe off? Because if these star factories at the edge of time are as extreme as Webb suggests, then our existing galaxy formation models might not just need small tweaks. They may need serious changes in how we treat star formation, feedback, and even the small-scale behavior of dark matter. So the next step is obvious. You take the standard cosmological model, the one with dark energy and dark matter that works so well on big scales, and you slam it against this new Webb data. Does it hold, or does it crack? That's where we go next, into the question of whether our simulations of galaxy formation are simply incomplete, or if Webb has just exposed a real weakness in how we've been modeling the universe. You've spent decades training supercomputers to grow a universe from simple early conditions, and then JWST shows you a version that seems to level up too fast. That's the tension right now. The basic framework still works, but the details of how and when galaxies form are under pressure. Start with what that basic framework actually is. The standard model of cosmology is usually called lambda CDM. Lambda is the dark energy term, the thing that makes the expansion of the universe speed up on large scales. CDM stands for cold dark matter, a form of matter that doesn't interact with light, moves slowly compared to the speed of light, and clumps under gravity. In this picture, structure forms hierarchically. Small dark matter halos collapse first, they pull in gas, they form the first small galaxies, those halos merge into bigger halos, and over billions of years you build up the massive galaxies and clusters we see today. On large scales, this model is not just okay, it is extremely successful. It explains the pattern of temperature fluctuations in the cosmic microwave background, the way galaxies are distributed across hundreds of millions of light years, and the overall age and composition of the universe. Before JWST, simulations based on lambda CDM also gave a reasonable match to the galaxy population we saw at lower redshifts, when the universe was a few billion years old and later. The expectation from those simulations was that if you look very early, say within the first 300 to 500 million years, you should mostly see small, faint protogalaxies. They should be there, but not too bright, not too massive, still in the early stages of growth. JWST comes in, looks at that time range, and starts reporting galaxies that are relatively bright and, by initial estimates, already fairly massive. Not huge by today's standards, but surprisingly grown up for that age. That is where the tension appears, not in the existence of galaxies, but in how advanced some of them look so soon. At first, this triggered a wave of impossibly massive galaxies headlines. People took early JWST data, fitted rough models to the light, and got high stellar masses that looked like clear conflicts with lambda CDM predictions. Over time, as more careful analyses came in, some of those masses were revised downward. Better measurements of redshift, better modeling of the stellar populations, and more realistic assumptions about dust all brought the numbers to a less dramatic range. But here's the important thing. Even after those corrections, the overall picture did not flip back to nothing unusual here. The extreme claims got toned down, but the basic trend stayed. There are more relatively bright, compact galaxies at very high redshift than many simulations predicted, and some of them still have star formation rates and stellar masses that push the limits of what the old recipes expected. So what do you do if the framework is good on large scales, but your small early pieces do not quite match? You don't throw out the whole model. You start tweaking the subgrid physics, the recipes inside the simulations that describe how gas turns into stars, how stars explode, and how they push gas around. One obvious lever is star formation efficiency. In many models, only a small fraction of gas in a given region gets converted into stars per unit time. That fraction is tuned so that by the present day, you get the right mix of galaxies. JWST's early galaxies suggest that in very dense early halos, star formation might have been more efficient. Maybe gas was clumping into dense regions faster, cooling more quickly, and collapsing into stars at a higher rate than in the later universe. Another lever is feedback. Massive stars and supernova dump energy and momentum into the surrounding gas. In simulations, this feedback is often what stops galaxies from turning all their gas into stars at once. It can blow gas out of small halos, heat it, and delay further star formation. If feedback in the earliest galaxies was less effective than assumed, or operated differently in those conditions, then more gas could stay in place and keep forming stars at high rates. That would naturally give you compact, intense starburst galaxies early on. Then there's the environment of dark matter itself. JWST is looking right at the regime where small-scale dark matter physics matters most, the first few 100 million years, when halos with masses much smaller than the Milky Way are collapsing, merging, and pulling in gas. LDCDM assumes dark matter is cold and collisionless, which sets a certain pattern for how small halos form and cluster. If the true behavior of dark matter is slightly different on small scales, for example, if it has some self-interaction, a tiny warm component, or other subtle effects, that could change how quickly these halos assemble and how they hold on to gas. Right now, most cosmologists aren't jumping to dark matter is wrong as the first explanation. The more conservative path is to see how far you can get by updating the gas and star formation physics inside the existing LDCDM framework. That means building new simulations that start from the same initial conditions, but use different star formation efficiencies, different feedback models, and different treatments of how gas cools and flows along cosmic filaments into early halos. The real test is this. Can you adjust those ingredients and end up with a simulated universe that still matches the cosmic microwave background and large-scale structure, but also produces enough bright, compact galaxies in the first 500 million years to match what JWST sees? If yes, then the core LDCDM model survives, and we just learned that early galaxy formation was more intense than we thought. If no, and the gap stays even after reasonable adjustments, then you start asking more radical questions about dark matter or even about the early expansion history. Either way, the message is not the model is dead, it's the model is stressed. LDCDM still explains the 93 billion light-year structure very well. It still gives you the correct age, the correct overall matter-energy balance, and the right patterns in the microwave background. Webb is not tearing that down. What Webb is doing is turning up the resolution on the smallest, earliest pieces of that structure and forcing us to admit that we did not fully understand how violent and efficient those first phases of galaxy growth really were. And that leads straight into the next big question. If early galaxies are forming stars this fast in this many places, then they're not just building their own structures, they're also flooding the universe with high-energy light. That light doesn't stay locked inside galaxies. It escapes into the space between them. So what does that do to the rest of the universe, to the vast sea of hydrogen gas left over from the Big Bang? And how does that help switch the cosmos from dark and opaque to bright and transparent? That's where we move from how galaxies form to how galaxies change the entire universe and into the chase for the end of the cosmic dark ages. Imagine a city covered in thick fog, and somewhere for the first time, a few streetlights flick on and start cutting through it. That's basically what JWST is watching, except the city is the whole universe, and the fog is hydrogen gas left over from the Big Bang. Here's the timeline in simple steps. Right after the Big Bang, the universe is hot, dense, and full of a plasma of protons, electrons, and photons all tangled together. Light can't travel far without bouncing off something. About 380,000 years in, the universe cools enough that electrons can combine with protons and form neutral hydrogen atoms. When that happens, light can finally move freely, and the glow from that moment is what we now see as the cosmic microwave background. After that, things get quiet in terms of visible light. There are no big galaxies yet, no bright stars everywhere, just slowly growing clumps of dark matter and gas. For hundreds of millions of years, there's basically nothing you would recognize as a bright object in the sky. That long stretch is what people call the cosmic dark ages. Space is filled with neutral hydrogen gas that can block high-energy light, and there aren't just many sources that can shine through it. Over time, gravity does its work. Gas falls into dark matter halos, cools, and eventually starts forming the first generations of stars. Those stars are hot and bright, and a lot of their energy comes out as ultraviolet light. When that light escapes their galaxies, it runs into the neutral hydrogen in the space between them. Now, here's the key change. When an ultraviolet photon from a star hits a neutral hydrogen atom, it can knock the electron off, ionizing that region of space. Do this enough and you turn that region of space from neutral to ionized. This process is called reionization, and it doesn't happen all at once. It's patchy and spread out in time. The current picture says that by redshift 6, which corresponds to about 1 billion years after the Big Bang, most of the hydrogen in the intergalactic medium is ionized again, and the universe becomes much more transparent to ultraviolet light. The big question is what exactly caused that transition, and how fast did it happen? This is where JWST comes in. It can see galaxies at redshift 7, 8, 10, and higher, right in the middle of this reionization era. It doesn't just take pictures, it takes spectra. When it looks at a galaxy from that time, astronomers study the emission lines, specific wavelengths of light produced by hydrogen, oxygen, and other elements. Some of those lines, especially the one associated with hydrogen's Lyman alpha transition, are very sensitive to how much neutral hydrogen is in the space between us and that galaxy. If there's a lot of neutral hydrogen still around, that line gets absorbed or heavily distorted before the light reaches us. If the space between us and the galaxy is mostly ionized, the line can come through more cleanly. So by comparing how strong or weak that line looks at different redshifts, you can get a handle on how much neutral hydrogen is still out there at each stage. JWST is built to pick up those faint signals from very distant, very young galaxies, and that lets us actually probe the state of the intergalactic medium during the end of the Dark Ages. Another thing we care about is how the ionized regions are arranged in space. When a young galaxy pumps out ultraviolet light, it doesn't ionize the whole universe. It carves out a bubble of ionized hydrogen around itself, a region where the fog has been cleared. Multiple galaxies in the same area can join their efforts, creating larger bubbles. Over time, as more galaxies form and shine, these bubbles grow and start to overlap. Eventually, the ionized regions connect and fill most of space, with only small pockets of neutral gas left. JWST's deep fields are one of the ways we try to map that process. In a single deep field, you look at a tiny patch of sky for many hours, collect galaxies at different redshifts, and study their spectra. You check how easily their light gets through, and you look for patterns. You want to see whether galaxies in the same region of the sky at similar redshifts show signs of living in big ionized bubbles, while others at the same time but in different directions might still be sitting in more neutral environments. Over scales of tens of millions of light years, this gives you a rough map of where the fog cleared first and how quickly it spread. All of this feeds into one blunt question. Who actually flipped the universe's light switch? Was reionization driven mainly by a huge number of tiny, faint galaxies that each contributed a little bit of ultraviolet light, or by a smaller number of brighter galaxies that did most of the work, or by early quasars powered by black holes? Hubble could only see the brighter end of the galaxy population at these redshifts, so the models had to guess what was happening with the countless smaller systems. JWST is now starting to see some of those fainter galaxies too, especially in its deepest and most magnified fields. If the faint galaxies are numerous and leaking enough ultraviolet light out of their gas and dust, they might dominate the reionization budget. If they are rarer or more sealed, with less light escaping, then the brighter galaxies and early black holes might carry more of the load. JWST's job is to measure actual escape fractions, star formation rates, and number counts, and to plug those into the energy balance of the early universe. The stakes are high because this isn't just a detail. It tells you how quickly the first structures grew, how clumpy matter was at early times, and how the environment changed for every later galaxy, star, and eventually planet. So with JWST, we're not just guessing anymore. We are directly watching the tail end of the Dark Ages and the rise of the first lights that punched holes in the cosmic fog. We're starting to see which galaxies were strong enough and numerous enough to reshape the entire observable universe from a dark, neutral medium into the transparent, ionized cosmos we live in now. But to really understand how all of that fits into the 93 billion light-year bubble you live in, you need more than individual stories. You need a full 3D map. Not just, here's a pretty picture of a deep field, but here's where these galaxies sit in distance and time, stacked on top of each other, so you can see the structure of the universe building up layer by layer. And that's exactly what happens when you take Webb's deep images, add redshifts, and turn those flat frames into a three-dimensional map of cosmic history. You stare at what looks like almost nothing, just a small black patch of sky with a few faint specks, and then you zoom in with JWST, and suddenly you're not looking at empty space anymore. You're dropping through thousands of galaxies stacked in depth. That's what a deep field really is. Not a wallpaper, but a vertical slice through billions of years of cosmic history. Here's how we get those slices. Observing time on Webb is extremely valuable, so teams design big survey programs to make the most of it. Two of the key ones are SEERS and JADES. SEERS, the Cosmic Evolution Early Release Science Survey, uses Webb to stare at a region that was already studied by Hubble and other telescopes. It stacks exposures for many hours in multiple infrared filters to pull out very faint galaxies that Hubble could not see. JADES, the Advanced Deep Extragalactic Survey, pushes even deeper in selected patches of sky, again integrating for tens of hours or more. The longer you stare, the more photons you collect, and the more faint, distant galaxies pop out of the noise. In these deep fields, every dot actually matters. When you see one of those images online and it looks crowded with tiny colored specks, you're not looking at stars in our own galaxy. You're mostly looking at entire galaxies, each one a city of suns. Some of them are relatively nearby on cosmic scales, a few 100 million light years away. Others are billions of light years out. The most distant ones in the frame can be more than 13 billion light years in present-day distance, with their light traveling for over 13 billion years to get to Webb. So that static is really a compressed view of the whole range of cosmic time in one direction. But a 2D image isn't enough if you want to build a map. To turn a flat, deep field into a three-dimensional structure, you need one more ingredient: redshift. For each galaxy, astronomers estimate or measure its redshift, that stretch in the wavelength of its light caused by the expansion of the universe. A higher redshift means you're seeing that galaxy further back in time, and in comoving terms at a larger current distance. So if you take the deep field image and then assign each galaxy a distance based on its redshift, suddenly you have depth. the pixels get layered. You can see which galaxies live in the nearby universe, which live in the Middle Ages of the cosmos, and which are sitting out in the early few 100 million years. In practice, there are two kinds of redshifts in play. Photometric redshifts come from comparing how bright a galaxy is in different filters, using the shape of its spectrum at low resolution. Spectroscopic redshifts come from splitting the light with instruments like NIRSpec and measuring the exact positions of emission or absorption lines. Photometric redshifts are quicker and can be done for thousands of galaxies at once, but they have bigger uncertainties. Spectroscopic redshifts are slower and require more observing time per target, but they are much more precise. Webb surveys use both, starting with photometric redshifts to build a rough 3D picture, then following up key galaxies with spectroscopy. Once you have that 3D information, a deep field stops being just a pretty picture and starts looking like a small, detailed chunk of the cosmic web. Even in a tiny area of sky, you can see patterns. Galaxies are not sprinkled randomly. They line up along filaments, form sheets, and gather in knots. In the early universe, these knots and filaments are the seeds of the structures that will later become galaxy clusters and superclusters. Webb is now resolving filaments and protoclusters at redshifts where the universe is only a few 100 million to a billion years old. Those protoclusters are important. When you see several galaxies at similar redshifts clustered in the same region of the sky, you're probably looking at a forming cluster, a high-density region of dark matter and gas where galaxies are growing faster and interacting more. Over billions of years, those structures will turn into the massive clusters we see today, spanning tens of millions of light years and containing thousands of galaxies. With Webb, you're catching them in the act of assembly, when they're still small and young, but already standing out from the background. Even the voids in a deep field tell you something. Regions with fewer galaxies at certain redshifts suggest underdense areas, where there was less matter to begin with. All of this fits into the idea of large-scale structure in miniature. In a single deep field, you can trace how the web of matter was already forming even when the universe was a fraction of its current age. Now, you have to keep the scale in mind. These deep fields that look so crowded are tiny on the sky. Some of the deepest pointings cover an area smaller than a fingernail held at arm's length. In that tiny patch, JWST can pull out thousands of galaxies, many of them at distances where previous telescopes saw little or nothing. If you then imagine tiling the entire sky with similar deep fields, you quickly get to enormous numbers. You're talking about hundreds of billions to trillions of galaxies within the observable universe, many of them faint and small, a large fraction only now coming into view with Webb sensitivity. This is where the idea of a 93 billion light-year wide observable universe starts to feel less abstract. Each deep field gives you a detailed sample of how galaxies are distributed along one narrow line of sight. By combining many such lines of sight across the sky and measuring redshifts for as many galaxies as possible, you can build a statistical 3D map of the contents of our bubble. You see how common different types of galaxies are at different times, how the rate of star formation changes, and how structures grow as you move from high redshift to low redshift. But there's a catch. If you want to turn these 3D maps into precise measurements of how the universe expands, how fast it's stretching, and how dark energy behaves, you can't just eyeball images. You need solid distance measurements, standard candles, standard rulers, and very careful calibration. Deep fields tell you what's out there. Turning that into exact numbers for the size, age, and expansion history of the 93 billion light-year wide bubble requires another step. So the obvious question is, if we're trying to measure something this big, with this much structure, what tools do we actually use as our yardsticks, and how does Webb help us update those tools to test whether our picture of cosmic expansion is really correct? To measure a 93 billion light-year universe, you need more than a ruler. You need exploding stars, subtle ripples in galaxy maps, and a telescope like JWST that can see far enough back in time to check whether your whole distance system is actually right. Without it, 46.5 billion light-years for the radius of the observable universe is just a guess. With it, it becomes a number based on real data. Let's start with how we even turn redshift into an actual distance. You can't fly out there with a tape measure, so cosmology uses a chain of tools called the distance ladder. On one side, you have standard candles, objects whose true brightness you think you know. On the other side, you have standard rulers, things whose true physical size you think you know. Both are used to calibrate how distance and redshift relate in the real universe. A classic standard candle is a Type 1a supernova. This is a kind of exploding star that usually happens in a binary system where a white dwarf star reaches a critical mass and blows up. The key point for you is that Type 1a supernovae have very similar intrinsic brightness once you correct for a few details. If you know how bright it's supposed to be and you measure how bright it looks from Earth, you can work out how far away it is. That lets you put a precise distance on the galaxy that hosted it. When you collect many of these supernovae at different redshifts, you get a distance-redshift relation that tells you how the expansion of the universe has changed over time. For standard rulers, one of the main tools is something called baryon acoustic oscillations. Early in the universe, before recombination, the plasma of photons and matter supported sound waves, pressure waves moving through the hot gas. When the universe cooled and neutral atoms formed, those waves got frozen in as a preferred scale in the distribution of matter. Billions of years later, when you map galaxies on very large scales, you can see a slight excess of galaxy pairs separated by that particular distance. That scale is your standard ruler. By comparing its apparent size at different redshifts, you can infer how distances grow with time as the universe expands. So you've got candles and rulers, and both of them line up with a cosmological model that includes dark matter and dark energy, but there's a catch. Most of the classic data for these methods comes from relatively nearby parts of the universe in cosmic terms, redshifts of 1 or 2, sometimes 3. To really stress test your model and to link it smoothly to what we see in the cosmic microwave background at redshift around 1100, you want to push these methods to higher redshift. That's where JWST's infrared vision comes in. Supernovae at high redshift are faint, and their light is redshifted out of the visible and into the infrared. JWST is designed to see exactly that light. It can detect and follow up distant supernovae, measure their light curves, and get spectra even when ground-based telescopes struggle because the light is too red and too weak. That extends the reach of Type 1a supernova cosmology deeper into the past, tightening the distance ladder and making it less dependent on big extrapolations. For galaxies in large-scale structure, JWST can observe galaxies that are too faint or too red for earlier surveys. That helps connect the high redshift galaxy population to the large-scale structure measured by other instruments. It also provides better calibration for things like how galaxy properties evolve with time, which feeds back into how we interpret both standard candles and standard rulers. Basically, Webb lets you anchor more points on the distance redshift curve between the local universe and the early universe. Now, there's a specific tension that people are worried about, the Hubble constant problem. The Hubble constant, often written as h0, is the current rate of expansion of the universe, how fast galaxies are moving away per unit distance. If you measure h0 using local methods like Cepheid variable stars and Type 1a supernovae in relatively nearby galaxies, you get one value. If you infer h0 from early universe data like the cosmic microwave background measured by Planck using the standard cosmological model, you get a slightly lower value. The difference is not huge, but it's bigger than you'd expect from random error, and it hasn't gone away. JWST can't solve that on its own, but it can help. On the local side, it can improve measurements of Cepheids and other distance indicators in dusty or crowded regions because its infrared vision cuts through dust and gives cleaner photometry. That makes the calibration of Type 1a supernovae more reliable. On the high redshift side, JWST can observe supernovae in galaxies further back, testing whether the relation between distance and redshift stays consistent with one simple expansion history or whether something odd is happening in the middle. If there's a subtle change in how dark energy behaves, or if some early universe effect we missed, it could show up as a mismatch between what we expect and what JWST actually sees. That leads directly to dark energy. In the simplest model, dark energy is just a constant energy density filling space, something like a cosmological constant. In that case, its effect on expansion is simple and predictable. But we don't know that it's truly constant. It could vary slowly with time. It could behave slightly differently at high redshift than it does now. To test that, you need very accurate distance redshift data over as wide a range as possible. JWST helps fill in the high redshift side, mapping how quickly distances grow at times when the first galaxies are forming. If dark energy were stronger or weaker in the past than our basic model assumes, or if it changed behavior at some critical epoch, that would change how big the universe is today for a given age. In other words, it would directly affect the conversion between 13.8 billion years old and 46.5 billion light-year radius. The 93 billion light-year figure is not just geometry. It comes from fitting a model to all these distance measurements, to the cosmic microwave background, to galaxy clustering, and then asking, given this expansion history, how far away are the farthest things whose light can reach us today? So when JWST helps refine supernova distances, when it ties galaxy surveys at high redshift to the large-scale structure we see now, and when it gives us a more precise look at how fast the universe was expanding at different times, it's indirectly refining that 93 billion light-year number. If the Hubble constant tension turns out to be a real sign of new physics, or if dark energy is not perfectly constant, then the exact size of our observable bubble could shift a bit. Not from 93 to 9, but enough that our map of everything gets a noticeable update. And that raises the next natural question. Now that you have better tools and a telescope that can reach deep into that observable volume, what exactly are you counting inside this 93 billion light-year bubble? How many galaxies? How many stars? What is the mix of matter and energy? And what does that really say about the universe you live in? Because once you start adding up the contents of this bubble, the numbers get so large that even with better yardsticks, they're hard to wrap your head around. Okay, you know the size, a sphere about 93 billion light years across. Now ask the blunt question. What actually lives inside that bubble? How much stuff are we talking about? And does it line up with what JWST is seeing? The short answer is, the numbers are ridiculous. Start with galaxies. When Hubble did its deepest surveys and astronomers extrapolated from those tiny patches of sky to the whole sphere, they got estimates that there could be up to around 2 trillion galaxies inside the observable universe. More recent work suggests the number might be lower, closer to a few hundred billion, but still, the key point is the same. You're not dealing with a few scattered islands, you're dealing with an enormous population. And a lot of those systems are not big spirals like the Milky Way. Many are small, faint, low-mass galaxies that Hubble simply could not see at most distances. JWST is finally starting to pick up those missing members, especially at high redshift, and that's tightening the estimate from a wild guess to data-backed range. Now drill down to stars. Each normal galaxy can host anywhere from a few million to 100 billion stars. Multiply that by hundreds of billions or more galaxies, and you land in a range of roughly 10 to the 22 to 10 to the 24 stars inside our observable bubble. In words, that's 10 billion trillion up to a septillion suns. Every one of those stars is a nuclear reactor, and many of them have planets. You don't need a precise number to see the point. Even at the low end of that range, the universe is saturated with stars on a scale that completely dwarfs anything human. But the raw count of stars and galaxies is only part of the story. Cosmology also keeps track of what all the energy and matter is made of, averaged across the whole observable universe. And when you add up all the evidence from the cosmic microwave background, large-scale structure, and supernova distances, you get a simple breakdown. Only about 4.9% of the total energy content is ordinary matter, the stuff made of protons, neutrons, and electrons, the kind of matter that makes you, planets, stars, and gas. About 26.8% is dark matter, which interacts through gravity but not with light. And the remaining roughly 68.3% is dark energy, a smooth component that drives the accelerated expansion of space. So even when you look at this enormous 93 billion light year bubble, most of what controls its fate is not the visible stuff. The galaxies and stars you see in Webb images are the bright trace of a much larger, mostly invisible energy budget. They ride on dark matter scaffolding, and their separation from each other is being stretched by dark energy. When you say this is what lives in the bubble, you have to remember that 3/4 of its content is invisible and only shows up through its effect on how things move and how space expands. Here's another counterintuitive point. On average, the bubble is almost empty. That sounds wrong when you think about trillions of galaxies, but you have to divide by the full volume, not by the few places where matter actually clumps. If you spread all the ordinary matter uniformly across the observable universe, you only get a few atoms per cubic meter of space. That average density is far lower than the best vacuums we can make on Earth, where even an ultra-high vacuum chamber still has far more particles per cubic meter than intergalactic space. The reason galaxies look so crowded is that gravity pulls matter into tiny regions compared to the overall volume. Most of your 93 billion light-year sphere is just extremely thin gas plus dark matter and dark energy. Inside galaxies, it's different. In a galaxy like the Milky Way, the average density in the disk is much higher, and inside stars, it's obviously enormous. But those are tiny zones compared to the total volume. If you try to sample the universe by randomly dropping a probe somewhere inside the observable bubble, the odds are overwhelming that you'd land in intergalactic space, not in a galaxy, not in a star system. From that perspective, galaxies are small, dense exceptions carved out of a mostly empty environment. Now, how does JWST change our understanding of what lives in this bubble? The big effect is at the faint, low-mass end of the galaxy population, especially at high redshift. Hubble could only see the brighter galaxies at very large distances. That meant that when astronomers tried to estimate the total number of galaxies, they had to guess how many small, faint ones they were missing, and what those galaxies were like. JWST sensitivity in the infrared lets it detect much smaller, less luminous galaxies at early times. That fills in the missing population that lives below Hubble's detection threshold. Once you know how many faint galaxies there are and how their numbers change with redshift, you can do a much better job integrating over the whole population. That improves estimates of how many galaxies exist, how many stars they form, and how much light they produce. It also feeds directly into questions about reionization, because those faint galaxies might be the ones that supplied most of the ultraviolet photons that ionized the early universe. If JWST shows that they are extremely common and very active, that tilts the balance. If instead they're rarer or more sluggish than expected, that pushes the responsibility onto brighter systems or early black holes. JWST also improves our view of the matter-energy mix indirectly. By observing galaxies at high redshift, it tests whether the growth of structure matches what you'd expect from a universe that is about 5% normal matter, about 27% dark matter, and about 68% dark energy. If the number and distribution of galaxies at different times lined up badly with that breakdown, you'd have to rethink the composition. So far, the broad picture still holds, but with Webb, the error bars on those cosmic inventory numbers can shrink, and small deviations might show up. So inside your 93 billion light-year bubble, you have somewhere between hundreds of billions and maybe up to a couple of trillion galaxies, something like 10 billion trillion to a septillion stars, a matter-energy mix dominated by dark stuff you can't see, and an average density that's only a few atoms per cubic meter. JWST's role is to stop us from guessing the details and actually show us the faintest, earliest pieces that we're missing from the count. But there's still a problem. Even with Webb, some of the most distant and smallest galaxies sit right at the edge of what a 6.5-meter mirror can detect. If you want to push deeper, you need more light. Since we can't build a planet-sized telescope, the question becomes, can we use the universe itself as part of the optics? Can we turn massive objects into natural magnifying glasses and use that to reach even farther into the bubble? That's where gravitational lensing comes in, and where JWST starts using entire galaxies and galaxy clusters as extra lenses to see things it could never reach on its own. You're literally using entire galaxies and galaxy clusters as magnifying glasses to peek deeper into the past than JWST could manage on its own. That's not a metaphor, that's how gravitational lensing actually works, and Webb is built to exploit it. The basic idea goes back to Einstein. General relativity says mass bends spacetime and light follows the curves. Put a huge mass, like a galaxy cluster, between you and the very distant background galaxy. The cluster's gravity warps spacetime enough that light from the background galaxy doesn't travel in a straight line. It gets bent, sometimes along multiple paths, and focused towards us. From our point of view, the cluster acts like a lens, magnifying and distorting the background object. If the alignment is right, you see a galaxy that normally would be too faint to detect, suddenly boosted by a factor of a few, or even 10 or more, depending on how close the line of sight passes through critical regions in the lens. Without that extra boost, those galaxies would sit below JWST's detection threshold even with long exposures. With the boost, they cross the line into "we can see you" and "we can even take a spectrum." That's a big deal because it opens up a population of very faint, very early galaxies that would otherwise be invisible, and those are exactly the ones that might dominate reionization and fill in the low mass end of galaxy formation. When you look at a strong lensing field in a Webb image, the visuals are obvious. The central cluster galaxies look fairly normal, but around them you see stretched arcs, thin curved smears of light, and duplicated little galaxies appearing in symmetric patterns. Those arcs are background galaxies whose light has been stretched along the direction of strongest magnification. Sometimes the same galaxy shows up as multiple images because light from it takes different paths around the cluster and arrives from slightly different directions. It looks strange, but it's not random. Astronomers take those distorted shapes and feed them into lens models, mathematical reconstructions of the mass distribution in the lensing cluster. By fitting the positions and shapes of the arcs and multiple images, they can figure out how mass must be arranged inside the cluster to bend light exactly that way. Once they have a good model, they can run it in reverse, de-lensing the images to estimate what the background galaxies really look like and how bright they really are before magnification. That modeling does two things at once. First, it lets you correct for the lensing so you can infer the true luminosity and size of the background galaxies. That's important if you're trying to count how many faint galaxies there are and how many photons they produce. Second, it gives you a map of the dark matter in the cluster. Most of a cluster's mass is dark matter, not stars. Lensing is sensitive to total mass, including dark matter, so the patterns in the arcs directly trace where the dark matter is concentrated. That's why gravitational lensing is not just a clever trick to see faint galaxies, it's also a physics tool. By mapping dark matter in many lensing clusters, you can test how it clumps on different scales, whether it's as smooth and collisionless as the basic cold dark matter picture says, or whether there are small deviations. On cluster scales, lensing data from JWST combined with Hubble and ground-based observatories help put limits on how dark matter behaves, how cuspy the inner profiles are, and how substructure is distributed. For JWST's main mission, probing the early universe, the key point is this: JWST plus gravitational lenses effectively gives you a telescope far larger than any mirror you could ever build. The 21-foot mirror collects the light, but the lensing cluster in front of it is doing the pre-magnification. Together, they let you reach to much smaller, fainter galaxies at higher redshift, and they do it inside the same 93 billion light-year observable volume we've been talking about. So you're not just passively looking at whatever happens to be bright enough, you're strategically picking lines of sight where the universe's own gravity helps you. That means you can probe deeper into the population of early galaxies, down into objects that are more representative of the bulk, not just the rare, bright outliers. But even with all that, JWST is still only seeing the lit-up parts of the story, the galaxies and stars. To really test the full picture of the universe, you have to connect those glowing structures to the initial conditions we see in a completely different kind of map, the cosmic microwave background, which shows the universe as a baby. The next question is, do those two maps, separated by 13.8 billion years of evolution, actually describe one consistent universe, or is there a mismatch that points to new physics? One instrument shows you the baby picture of the whole 93 billion light-year universe. The other shows you the toddler's first steps. The cosmic microwave background is that baby photo, and JWST is now watching the same universe a few 100 million years later, starting to build galaxies. The question is simple and brutal. Do those two views line up, or is something off in between? First, what is the cosmic microwave background really? About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen. Before that, the universe was a hot plasma, where light could not travel far before scattering. After recombination, light was suddenly free to move almost unhindered. The glow from that moment has been traveling ever since, stretched by expansion from high-energy radiation down to microwaves. Today, we see it as a nearly uniform background of microwave light coming from every direction in the sky. That light isn't perfectly smooth. If you map its temperature across the sky, you see tiny variations, differences of a few parts in 100,000. Those small variations in temperature correspond to small variations in density, places where the matter was slightly more or slightly less concentrated than average. That map is the CMB, the cosmic microwave background, and it is effectively a snapshot of the whole observable universe when it was just 380,000 years old. Satellites like WMAP and later Planck made extremely precise maps of that pattern. By analyzing how strong those fluctuations are on different angular scales, cosmologists can infer key properties of the universe. From that data and the physics of the early plasma, we get the age, about 13.8 billion years. We get the geometry, very close to flat on large scales. We get the matter-energy breakdown. How much ordinary matter, how much dark matter, how much dark energy. The CMB is the main reason we quote those specific numbers with confidence. Now, here's the important connection. Those tiny density fluctuations you see in the CMB are the seeds of everything JWST is now imaging. Slightly denser regions had a bit more gravity, so over time they pulled in more matter, growing into filaments and knots. Dark matter clumped first, forming halos. Gas fell into those halos, cooled, and eventually formed stars and galaxies. Give the universe a few 100 million years after recombination, and those subtle ripples in the CMB grow into the first galaxies at redshift 10, 12, 14, the ones JWST is now catching in deep infrared images. So when you look at a JWST deep field full of early galaxies, you're not looking at a separate story. You're seeing the later frame of the same system whose birth picture is the CMB. The CMB tells you what the initial conditions were. JWST tells you what those conditions produced after hundreds of millions of years of gravity and expansion. It's one universe, two different phases. This is where simulations become the bridge. Cosmologists take the initial conditions inferred from the CMB, basically a 3D field of tiny density fluctuations, and they feed it into supercomputer simulations. They include dark matter, gas, basic physics of cooling, star formation recipes, and feedback from stars and black holes. Then they let the simulated universe evolve for 13.8 billion years of cosmic time. At each stage, they can pause the simulation, take a snapshot, and see what the universe should look like at a given redshift. If the model is right, the simulated universe at redshift 10 to 14 should have a population of galaxies that looks statistically similar to what JWST sees at those redshifts. Same basic number densities, similar mass distributions, similar star formation activity. It doesn't have to match galaxy by galaxy, but the overall pattern should line up. The same goes for lower redshifts, mid-age galaxies, and present-day structure. The CMB locks in the starting conditions and the overall cosmological parameters. JWST and other surveys check the later stages. Right now, large-scale structure and the CMB match very well. On scales of tens to hundreds of millions of light years, the lambda CDM plus those initial conditions reproduces what we see. JWST is probing much smaller scales and much earlier times, and that's why the possible tension appears. As we talked about earlier, some JWST observations suggest galaxies at high redshift are more abundant, more massive, or more active than expected in many simulations that start from CMB-based initial conditions. If that mismatch holds up after all the details are checked, then you have a problem that goes beyond just we misjudged the star formation parameter. It starts to look like a sign that either the small-scale physics in the simulations is incomplete or that the cosmological model needs an update. Maybe dark matter isn't perfectly cold and collisionless on all scales. Maybe there was an extra phase of early dark energy that altered the expansion rate or growth of structure in the first few 100 million years. Maybe some assumption about how gas cools or how primordial stars form is significantly off. The stakes are high because the CMB and JWST sit at opposite ends of the timeline. The CMB nails down the universe as a baby, giving you precise numbers. JWST shows you the toddler phase when the first galaxies and black holes switch on. If you can run one continuous model that takes you smoothly from the CMB to JWST and then to the present, with no big discrepancies, that's a huge win for our understanding. If you can't, and the best model that fits the CMB simply can't produce the early galaxy population JWST sees, even after reasonable adjustments, then something in the physics is missing. That's why every new high redshift galaxy JWST confirms, every refined mass estimate, every new measurement of star formation at early times matters more than it might seem. Each one is a test case. Does this object fall within the predicted range for that epoch, or does it sit out on the edge, forcing the models to stretch? A few outliers are fine. A pattern of outliers across different surveys and fields is a sign that the underlying theory is not capturing some important effect. So you now have two maps of the same 93 billion light-year bubble, one from when it was 380,000 years old, and one from when it is a few 100 million years older. JWST's job is to fill in the gap between those maps and see whether the story they tell is consistent. If it is, we get even more confidence in our picture of dark matter, dark energy, and cosmic history. If it isn't, we may be looking at the first clear hints of new physics and how the universe built its structure. But even if you perfect that model, there is still a hard limit you cannot cross. No matter how good JWST gets, no matter how well the CMB is mapped, there's a boundary you will never see beyond, a real horizon built into space-time itself. And that's the next step, facing the ultimate wall of what you can ever know about the universe. Even if you had perfect telescopes, infinite time, and unlimited technology, there's a hard edge to your universe, a boundary you can never look past. Not because the objects beyond it are too faint or too small, but because no signal from them has had time to reach you. Beyond that edge, the cosmos is literally unknowable. This edge has a name, the particle horizon. In plain language, it's the maximum distance from which light could have reached you since the Big Bang, given how the universe has expanded. You start the clock at time 0, you let the universe expand and stretch for 13.8 billion years, and you ask, from how far away could a photon, traveling at the speed of light the whole time, realistically make it here? When you include expansion properly, the answer today is a radius of about 46.5 billion light-years. That's the radius of the observable universe we've been talking about. That number isn't just speed of light times age. If the universe were static with no expansion, the horizon would be 13.8 billion light-years. But because space itself has been stretching while the light was in flight, the regions that emitted the oldest light we see are now much farther away than 13.8 billion light-years. So you get a radius horizon of about 46.5 billion light-years, and the full diameter of the observable bubble is about 93 billion light-years. Everything you can possibly see in any direction sits inside that sphere. Now here's the crucial point. That horizon is not the edge of space. The universe does not stop there. It doesn't cut off, and there's no physical wall. Space almost certainly continues beyond your particle horizon. The laws of physics we know, plus the uniformity of the cosmic microwave background, strongly suggest that beyond our observable bubble, there are more galaxies, more stars, more structure, and possibly other observers asking the exact same questions. But no light, no particle, no gravitational wave, nothing from those regions outside your horizon has had time to get here. And in many cases, because of ongoing expansion and dark energy, nothing ever will. So when we say this is the observable universe, we're not describing everything that exists. We're describing everything that can ever send a signal to you. Beyond that, the universe keeps going. But for you, it's not just unknown, it's permanently inaccessible. No clever trick, no new wavelength, no bigger mirror changes that. This idea ties directly into inflation, the theory that in the very tiny fraction of a second after the Big Bang, the universe went through a phase of extremely rapid expansion, much faster than the speed of light in terms of how fast distances grew. That sounds like it breaks the rules, but it doesn't, because it's space itself expanding, not objects moving through space faster than light. Inflation takes a tiny, causally connected patch of the early universe and blows it up to a region that is vastly larger than our observable bubble today. If inflation really happens, and the evidence from the CMB strongly supports that, then the part of the universe we can see now is just a tiny fraction of the total universe. The full universe could be many orders of magnitude larger than our observable sphere, or even effectively infinite. Our 93 billion light-year bubble would be like a small neighborhood inside a city you will never see the edge of, because the light from most of it will never reach you. It's important to separate that early super-fast expansion from what you can do now. Inflation happened when the universe was extremely young and has long since ended. The current accelerated expansion driven by dark energy is much slower, but it still has a key effect. It creates a kind of event horizon for the future. Some distant galaxies are already receding us so fast due to the expansion of space that light they emit today will never reach us, not even if you wait forever. They are still inside our current particle horizon, but given how fast the expansion is accelerating, new light from them is effectively lost to us. This is the hard limit. No telescope, not even JWST or anything that comes after it, can beat relativity. You can't see past the particle horizon because past that, no signal has had time to arrive. You can't cheat the future event horizon because expansion is pulling some regions away faster than light in terms of separation speed, and relativity says you can't catch up or pull information back once it's beyond that boundary. Making a bigger mirror only helps us see fainter things inside the horizon, not beyond it. So when you think about the 93 billion light-year number, don't treat it like the size of everything. Treat it as the size of the universe you are allowed to interact with. For you, for physics, for any experiment you can ever run, this bubble is the universe. Every observation in cosmology, every galaxy image, every spectrum, every CMB measurement, all of it is drawn from within that finite sphere. The rest of whatever exists beyond it is permanently outside your data. That might sound limiting, but it's also what makes cosmology a real science instead of pure speculation. We have a defined, observable region of space-time with a measurable size, measurable content, and measurable history. Inside that region, we can test models, break models, refine them, and build a detailed picture. Outside it, we can only infer, never confirm. So then the question becomes, knowing that we're trapped inside this 93 billion light-year laboratory, how far can we push our instruments before we hit practical limits? And what comes after JWST? Do we just keep making slightly better versions of the same thing? Or is there a next wave of telescopes and observatories that will change the game again, the way Webb did after Hubble? Because if JWST is not the final word, but only the first step in a new era of precision cosmology, then the next machines we build will decide how much more of this bubble we can turn from beautiful pictures into hard, testable physics. You think JWST is the final boss, but it's actually the opening level of precision cosmology. Webb showed us what's possible when you go all in on one deep, cold infrared machine. Now the next wave of instruments is coming, and together they're going to turn this 93 billion light-year bubble from we can see it into we can measure almost every part of it with different tools. Start with the Nancy Grace Roman Space Telescope. Think of Roman as the wide-angle partner to JWST's zoom lens. Roman will have a mirror smaller than Webb's, more in the Hubble class, but its real power is the field of view. Where JWST looks at tiny regions very deeply, Roman is designed to image huge chunks of sky at once. Its wide-field instrument will be able to map large areas with Hubble-like sharpness in infrared. That means you can do precise surveys of billions of galaxies, not just thousands, and measure how they're distributed on large scales. Why does that matter? Because dark energy shows up in how structure grows and how distances scale with redshift over cosmic time. Roman will measure subtle patterns like weak gravitational lensing, tiny distortions in galaxy shapes caused by foreground mass, and baryon acoustic oscillations in the distribution of galaxies. Those data sharpen our measurements of how fast the universe has been expanding and how dark energy behaves. The same telescope will also hunt exoplanets via microlensing, watching for brief brightening events when a star and its planets pass in front of a background star. So Roman covers both ends, the large-scale expansion of the universe and the small-scale census of planets. Now look back down to Earth because the ground game is getting a massive upgrade too. Over the next years, 30 to 40 meter class telescopes are coming online. The extremely large telescope, the 30-meter telescope, and the giant Magellan telescope. A 30-meter mirror is about 98 feet across, about 30 meters, far bigger than anything we've flown in space and far bigger than current 8 to 10-meter ground telescopes. With adaptive optics to correct for the atmosphere, these giants will deliver incredibly sharp images and spectra from the ground. These telescopes won't replace JWST, they'll complement it. Webb is perfect for finding interesting targets at high redshift, picking out compact galaxies, early black hole candidates, and strange objects in the infrared. The LT, TMT, and GMT can then zoom in with ultra-high-resolution spectroscopy, separating light into extremely fine wavelength slices. That lets you measure detailed velocity fields, see how gas is moving inside galaxies, measure black hole masses in galaxy centers, and analyze the chemical makeup of stars and gas in a level of detail Webb doesn't have time or resolution to do for everything. Webb says, "Here are the objects." The giant ground-based telescopes say, "Here is exactly what's going on inside them." Then there's ALMA, the Atacama Millimeter Submillimeter Array sitting high in Chile's Atacama Desert. ALMA doesn't look at optical or infrared light. It observes millimeter and submillimeter wavelengths, which are perfect for tracing cold gas and dust, the raw fuel for star formation. When Webb finds a high redshift galaxy like Jade's GS Z14 and shows that it's bright and young, ALMA can point at the same object and look for specific emission lines from elements like oxygen and carbon in the cold gas. That's how we know that only a few 100 million years after the Big Bang, some galaxies already contain enriched material. ALMA fills in the other half of the story. Not just the stars you see glowing, but the gas and dust reservoirs that will feed the next wave of star formation. Put that together and you get a multi-wavelength view. JWST in infrared, Roman wide field in infrared, LT, TMT, and GMT in optical and near-infrared with extreme detail, ALMA in millimeter bands. Each one covers a different temperature range and a different physical component: hot stars, warm dust, cold gas, large-scale structure. None of them alone is enough. Together, they give you a much more complete picture of how galaxies live, grow, and die across the entire observable universe. And we're not stopping at light. The future is a full multi-messenger universe. Gravitational wave observatories will keep improving beyond LIGO and Virgo. Planned detectors, both on the ground and in space, will pick up waves from merging black holes and neutron stars across a wide range of masses and distances. Those mergers are connected to star formation, galaxy evolution, and black hole growth, all the things JWST is already mapping visually. If you can see a galaxy where massive stars are forming and in the same cosmic era detect gravitational waves from the endpoints of those stars, you start to link the life cycles together in real data. Neutrino detectors will join in too. Neutrinos are almost non-interacting particles produced in huge numbers by supernovae, nuclear reactions, and other high-energy events. Future large neutrino observatories could detect bursts from nearby supernovae, or even a diffuse background from many past explosions. That adds another channel to probe how often stars die, how they explode, and how they enrich galaxies with heavy elements. When you combine all of this, JWST's deep infrared imaging and spectroscopy, Roman's wide field mapping, LT, TMT, and GMT's extreme resolution from the ground, ALMA's millimeter view of cold gas and dust, gravitational waves tracing compact object mergers, neutrinos tracing violent events, you stop thinking of the observable universe as a distant scenery. It starts to look like a lab. You have multiple instruments probing different aspects of the same 93 billion light-year bubble, cross-checking each other and feeding into the same models. We're moving from we can take pictures of galaxies to we can measure how matter, radiation, and space-time interact across almost the entire history of this bubble. The uncertainties shrink, the free parameters get cornered, and the space of allowed theories get tighter. That's what precision cosmology really means, using every tool you can build to turn this enormous, seemingly unreachable volume into something you can test, constrain, and model with actual numbers. And after all of that, there's one more angle we haven't really hit yet. Even if you map the bubble, measure its contents, and track its history, you're still stuck on one tiny planet. Your physical reach is microscopic compared to 93 billion light-years. So what does all of this mean for a human lifetime and for a civilization that will never cross it but can now measure it? That's where we finish, with the question of what a 93 billion light-year universe actually means for a human lifetime, and for a civilization that will never cross it but can now measure it. After all this, you're still a human on a rock, moving slower than a cosmic snail in a universe you will never cross. That's the blunt reality. You live inside a 93 billion light-year bubble, and your physical travel record, even in theory, barely scratches it. So let's be generous. Imagine you somehow build a ship that can cruise at 10% of the speed of light. That's around 18,600 miles per second, way beyond anything we can do right now, but still allowed by physics. At that speed, in 1 year, you cover about 0.1 light year. In 10 years, 1 light year. In 1,000 years, 100 light years. Now compare that to the radius of the observable universe, about 46.5 billion light years. Even if you rode that ship non-stop for the entire current age of the universe, around 13.8 billion years, you'd cover about 1.38 billion light years. That's only a few percent of the radius, and an even smaller slice of the full 93 billion light year diameter. And of course, you don't live billions of years. A human lifetime at that speed would barely get you to the outskirts of your own galaxy, let alone out into the wider cosmos. Now, drop back to what we've actually done. The farthest any human has traveled is the moon, roughly 240,000 miles away, around 386,000 kilometers. In terms of light travel time, that's about 1.3 seconds. That is the total radius of human crewed exploration, 1.3 light seconds. The farthest probe, Voyager 1, is out at about 15 billion miles, around 24 billion kilometers, which is on the order of 22.5 light hours, not even a full light day. Put that next to 93 billion light years, and the comparison is almost meaningless. Our physical footprint is a microscopic dot at the center of this enormous sphere. So physically, you are stuck in a tiny neighborhood, but observationally, you're everywhere. With telescopes, you've already spanned the whole bubble. CMB satellites like WMAP and Planck map the entire sky in microwaves, giving you the baby picture of the full observable universe. Large ground-based surveys mapped millions of galaxies across billions of light years in optical and infrared. JWST now punches deep tunnels through the early universe, right back to the first few 100 million years. Combined, these instruments let your species build a 3D map that covers almost the entire observable sphere in time and space, even though your bodies hardly leave home. That's the weird contrast. Your ships crawl, but your data flies. Photons do the traveling for you. When you look at JWST images, CMB maps, galaxy surveys, you're not looking at pretty pictures in a casual sense. You're looking at measurement devices frozen into images. Each pixel carries numbers, intensities, wavelengths. Each spectrum carries redshifts, line strengths, and chemical fingerprints. Those numbers feed into models that test gravity, dark matter, dark energy, and the whole expansion history of the universe. Take a JWST deep field. To a casual viewer, it's a beautiful shot of colorful galaxies. To a cosmologist, it's a table of data. Thousands of objects with positions, brightness profiles, and estimated redshifts. You can turn that into a statistical test of how many galaxies exist at each epoch, how fast stars formed, how structure grew. You can check whether the counts match what lambda CDM predicts, or whether you see systematic deviations. The same goes for the CMB, which looks like a fuzzy color map, but is actually a precise chart of temperature differences you can expand into mathematical functions and compare to theory. This is why the 93 billion light-year universe is not just a fun fact. The size, the contents, the expansion rate, the composition, all come from squeezing as much information as possible out of the light that has crossed that bubble. You're not just staring at the sky. You're running an experiment at the largest possible scale, using the whole observable universe as the system under study. Your detectors sit on one small planet, but the apparatus is everything inside the particle horizon. And here's something easy to overlook. You live at a very convenient moment for this kind of work. The universe is old enough that galaxies, stars, and planets have formed everywhere. It's transparent. The intergalactic medium is mostly ionized, so light from distant sources can travel to you. At the same time, it's still young enough that the cosmic microwave background is visible, not redshifted into wavelengths so long that you couldn't detect it with realistic technology. You can see both the afterglow of the Big Bang and the fully developed cosmic web in one era. That timing matters. If you lived much earlier, before reionization finished, large parts of the universe would still be fogged out by neutral hydrogen, and distant galaxies would be harder to see. If you lived much later, dark energy would push more and more galaxies beyond your event horizon. Their light would never reach you, and the CMB would be stretched further and further, fading into an almost undetectable background. The accessible universe would shrink in practical terms, even if the physical bubble kept growing. Right now, you're in a sweet spot. Enough time has passed for complexity to emerge, but not so much that the evidence has been erased or pushed out of reach. JWST is one of the first tools built to fully exploit that moment, to grab as much information as possible before cosmic expansion hides it. So when you hear 93 billion light years, don't file it on their random huge number and move on. That number represents the scale of the experiment you're sitting inside. You're not just in a big universe. You are inside a precisely measured 93 billion light-year wide test of physics. And you are alive at the stage where we can still read both the beginning and a large part of the story in the same sky. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.